In the previous video, we saw that writing the complex numbers in polar form makes it very easy for us to multiply. Now we look at an interesting conclusion, a consequence of what we just saw. If given any complex number, it can be written in the polar form. Now what is z squared? It's z times z, so by our rule it should be r squared cosine theta plus theta and I sine theta plus theta, which is just r squared cosine 2 theta plus I sine 2 theta. Similarly, z cubed would then be this result multiplied by this, which the r's multiply to give r cubed and the angles add. So theta plus 2 theta gives me 3 theta. I sine 3 theta. Similarly, this is r4 cosine 4 theta plus I sine 4 theta. You can see the pattern and see where this goes. In general, if you take a complex number and you multiply by itself n times, meaning you take the nth power, what you get is r to the power n cosine n theta plus I sine n theta. And this is a very useful and powerful result, and it has a name. It's called Moivre's theorem. Example, let's say you want to find this. Now recall, one way to do this from Math 103 is to use the binomial expansion. You can shorten that out using Pascal's triangle, find the coefficients, find all those 10c1, 10c2 terms, figure out the powers and all, which can be complicated. Here's how we can do it in an easier way. So let z equals 1/2 plus 1/2 I. I'm going to write this in polar form. Okay. To write in polar form, I need r. That's going to be that. So square root of 1/4 plus 1/4, square root of 1/2, which is 1 over square root of 2. And my angle is going to be tan inverse of 1/2 over 1/2, which is pi over 4. So z is just 1 over root 2 cosine pi over 4 plus I sine pi over 4. And what I'm trying to find is z to the power 10, and that's just going to be 1 over root 2 to the power 10 cosine of n times the angle. So 10 pi over 4 plus I sine 10 pi over 4. This is 1 over 2 to the power 5 because square root means the exponent is 1/2 and 1/2 times 10 is 5. Cosine of 5 pi over 2 plus I sine 5 pi over 2. Now in fact I can make this even simpler because I know from the graph of cosine that at multiples of pi over 2 where the 2 doesn't cancel out, meaning odd multiples of pi over 2, it's 0. And sine at odd multiples is 1. So this is just I over 2 to the power 5. And I can do all of this computation without having to use the binomial expansion, which would give the exact same result, but it would be of no use at all, in the sense that it would be really lengthy. This idea of taking n powers of a complex number has an application, which we're going to start by a concrete example of finding cube roots of 1. Now so far in Math 103 and any other place you have encountered cubic equations, when you end up with x cubed equals 1, you say x is 1. Or if you have x cubed equals -1, then x is -1. However, if instead of cube, if you have a square, then you get two solutions, right? You get a positive and negative. And this number of solution 2 matches with this power of x, which is 2. Similarly, if you have x equals 1, you have one solution, which matches with the exponent of x. So, natural question to ask is, well, what happens here? Why does it not have 3 solutions if x is power 3? So in fact, it does. It just happens that the other 2 are complex numbers, so we don't consider them. So we're going to find this using 2 different methods. In this video, I'm going to use method 1, which I'm calling the Math 103 difference of cubes method. And then next video, we use a different method to solve it. So remember, difference of cubes factors this way. So if x cubed minus 1 is 0, then I have x minus 1 times x squared plus x plus 1 is 0. So these are product of 2 things. So either x minus 1 is 0 or x squared plus x plus 1 is 0. This gives me x is 1. And that's what you're familiar with, right? X equals 1 and 1 cube is 1 and 1 cube minus 1 is 0. But there's also this quadratic equation where I can use the quadratic formula to get x, it's negative 1, plus minus square root of 1 minus 4 over 2, which essentially becomes root 3I over 2. There's a plus version and a minus version. And these are complex numbers. And the claim is that these complex numbers are such that their cubes are also equal to 1. Let's check. I'm going to check for one of them and then let you check for the other. Let's say I check for this one. How do I do that? Well, cubing this means I look at the polar form because that's going to be easy. The absolute value of this is square root of 1/4 plus 3/4. That comes out to 1, which is nice. The angle is tan inverse of root 3 over 2 times 2 over negative 1. So it's negative root 3. Where is this point? This point is in quadrant 2. Now tan inverse of just square root of 3 is, let's see, sine is 1/2 times 2 over root 3. So it should be 60 degrees, pi over 3. In quadrant 2, that would be pi minus pi over 3, 2 pi over 3. So in polar form, z is cosine of 2 pi over 3 plus I sine 2 pi over 3. Let's verify. Then z cubed would be cosine of 3 times 2 pi over 3 plus I sine 3 times 2 pi over 3. Cosine 2 pi is 1, sine 2 pi is 0. So, in fact, it is true that this is a solution to this equation. Because when I cube this, I get 1. So that sort of solves the mystery of why when you have x cubed equals 1, you only say that x equals 1. It's because usually we are working just with real numbers. The takeaway here is that when you allow for complex numbers, cube roots of 1 has not 1 but 3 solutions, 2 of which are complex number. Now try this and verify that it's true even for this complex number. That's the end of this video. The next video we look at another approach to find this. I sort of already covered that approach here, but anyways, we're going to look at it even then. And then we're going to look at a general process for finding cube roots when you allow for complex numbers.